Hello guys, welcome to this special Maths Halloween edition video. Today we're going to find the area of this pumpkin using calculus. In fact, this pumpkin is described by an equation. And this is the equation that describes our pumpkin. It might seem scary and difficult at first, but it is just three equations combined together to give us this pumpkin. As you can see from this picture, those are just three ellipses. So they're basically the same ellipse but moved in the xy plane. So we have to find a way to find the area of this pumpkin. And what can we do? Well, whenever we have equations in an xy plane, we need calculus. And in particular, we're going to do it using integrals. So let's go straight to our blackboard and let's try to find this area. Okay guys, as you can see, I'm not using my usual background because we have a lot of things to write down and I don't want to erase the blackboard every 2 seconds, so I'm gonna use this background. So guys, let's start. We have this equation that describes our three ellipses, and those three are the equations of the three ellipses. This is the first one that is here, E1, this is the second one, that is this, E2 and E3. Now, how can we find the area of the entire pumpkin? Notice that we divide this pumpkin in 4 pieces. This piece is equal to this one, that is equal to this one, that is equal to this one. So their areas has to be the same. So we know that the area of the entire pumpkin is 4 times the area of 1/4 of the pumpkin. In other words, let's just find the area of 1/4 of the entire pumpkin, and if we multiply it by 4 we get the area of the entire pumpkin, just to make calculations easier. So what is the area of 1/4 of this pumpkin? Well, it could be the sum of this area right here plus this green area here. So this equals 4 times the area, the blue area, plus the green area. And how can we get those? As you can see, they are areas under a curve. So we have to find some equation, and using integrals we can find those areas. In particular, let's first focus on the blue area because it is simpler. We know that this is the area under this curve, and this curve is half the area of our ellipse. And since the three ellipses are the same, is equal to the area of this ellipse. So it's always better to work with the second ellipse, and we want to make calculations as easy as possible. So it is better if we work with the ellipse in the middle, because the equation is simpler. Now we have to find the function y. In other words, we have to isolate the variable y. So let's do it. 4x squared plus y squared minus 25 equals 0. So y squared equals 25 minus 4x squared, square root to both sides, we get that y equals plus or minus the square root of 25 minus 4x squared. And why do we have this plus or minus? Because this ellipse is not described by just one function. It is described by this function with the plus sign and this function with the minus sign. But since we are working with this one, we just need the function with the plus sign. So the blue area is equal to the yellow area. So the blue area equals the yellow area. That is the integral from minus h to h. If we call this point minus h, this point h, of our function, so the square root of 25 minus 4x squared dx. Then we're going to find those minus h and h to solve the integral. But first, let's try to find what is the green area. Now we need to find the green area, and how can we do it? Well, we can write it as the sum and difference of two areas. And the first one is this blue area here minus this yellow area here. So our green area equals the integral from 0 to h of the square root of 25 minus 4x squared dx minus this yellow area, and we can even write this yellow area as 2 times half of the yellow area. That is the integral from this point, for example a, to h. So the integral from a to h multiplied by 2 of the square root of 25 minus 4x squared dx. Now we have a formula for the green area and a formula for the blue area. And let's do another thing to make things easier. Since the ellipse is symmetric, as you can see, this part here is equal to this part here, we can write this integral as 2 times the integral from 0 to h of the square root of 25 minus 4x squared dx. We have to do this to make things easier. Now we have to find what a and h are equal to. Well, h is just when the function is 0. In other words, we have to find x such that 25 minus 4x squared equals 0, and 25 minus 4x squared equals 0. So we know that x equals plus or minus the square root of 25 divided by 4, and this equals plus or minus 5 over 2. Since the function is 0 when x equals plus or minus 5 over 2, we know that h equals plus 5 over 2, because we call minus h this point here. Now we have h, and we have to find a. A is the value of x when the second and the third ellipse are equal to each other, so the intersection of the two. So we know that the function that describes this is the square root of 25 minus 4x squared when y is positive, and we have to do the same for this one, that is the third ellipse. And if we isolate y, here we get that y equals the square root plus or minus, but we just consider the positive function. So the square root of 25 minus 2x minus 5 squared. I did the same thing I did earlier to find y. Now we have to find x when those two are equal to each other. In other words, we have to find x such that 25 minus 4x squared equals the square root of 25 minus 2x minus 5 squared. We can square both sides, so 25 minus 4x squared equals 25 minus, and this is 4x squared minus 20x plus 25. 25 minus 4x squared equals 25 minus 4x squared plus 20x minus 25. As you can see, we can simplify minus 4x squared and minus 4x squared, and the same thing for 25, and we get that 20x minus 25 equals 0, and this equals 0 when x equals 25 over 20, and 25 over 20 is 5 over 4, and we know that a equals 5 over 4. So guys, let's substitute a and h. So see, this is 2 times the integral from 0 to 5 over 2 of the square root 25 minus 4x squared dx. So this equals the integral from 0 to 5 over 2 of the square root of 25 minus 4x squared dx minus 2 times the integral from a, that is 5 over 4, to 5 over 2 of the square root of 25 minus 4x squared dx. Hey guys, now we have all the equations. We need to find the area of the pumpkin, and it might seem difficult now to solve these integrals, but it is not. But since we have a bunch of integrals, definite integrals of the same function, it is better if we first find the antiderivative of this function, just to make things easier and faster. So the antiderivative of 25 minus 4x squared is what we need to find first. And how can we do this? Well, whenever we have under the square root a quantity squared, in this case 5 squared, and this, that is 2x squared, well, we can use a trig substitution. In fact, if we have a right angle triangle like this, if this side has length 5 and this has length 2x, this that we call r as length as the square root of 25 minus 4x squared using the Pythagoras theorem. And if this angle is theta, we know that 5 times sine theta equals 2x, and 5 times cosine theta equals r. And to do our substitution, we have to find the x. We know that x equals 5 over 2 times sine theta, and we can differentiate both sides, and dx equals 5 over 2 times cosine theta d theta. We can do our substitution, so this equals the integral of all of this is just r, that is 5 times cosine theta, so 5 times cosine theta times dx, that is all of this stuff. So 5 over 2 times cosine theta d theta. And we can bring the constants outside, and this is just 25 over 2 times the integral of cosine squared theta d theta. Now, how can we find the antiderivative of the cosine squared of theta? Well, this is where Werner's formulas comes into play. In fact, we know that cosine squared of theta equals cosine of theta times cosine of theta, that equals 1/2 times the cosine of theta minus theta as the cosine of theta plus theta. So this equals 1/2 times the cosine of theta minus theta is the cosine of 0, that is just 1. So 1 plus the cosine of theta plus theta is the cosine of 2 theta. So let's do our substitution. This equals 25 divided by 2 times the integral of 1/2 times 1 plus the cosine of 2 theta d theta, and this equals, we can bring the 1/2 outside the integral sign, so this is 25 over 4 times the integral of 1 plus the cosine of 2 theta d theta, and this equals 25 over 4 times, we can split this integral in two integrals, so the integrals of 1 d theta plus the integral of the cosine of 2 theta d theta. So this equals 25 over 4 times the integral of 1 d theta, just theta, plus the integral of cosine of 2 theta d theta. Now to solve this integral, we can do a simple substitution. So let t be equal to 2 theta and differentiate both sides. So t equals 2 times d theta, and d theta equals dt divided by 2. Let's make our substitution. So the integral of the cosine of 2 theta d theta is just the integral of cosine of t over 2 times dt. This equals 1/2 times sine of t plus the constant of integration c. But we don't need the constant of the integration because we are doing all of this to find a definite integral, so we don't need the plus c, and this equals 1/2 times the sine of 2 theta. Okay guys, since we know that this integral is 1/2 times sine theta and we don't need the constant of integration c, this is 25 divided by 4 times theta plus 1/2 times sine theta, and this equals 25 over 4 times theta plus 25 over 8 times sine of theta. So we now know that this integral is this, but we have this as a function of theta, but we were integrating respect to x, so we want this as a function of x. So remember that 5 times sine theta equals 2x. So knowing that 5 times sine of theta equals 2x, we can isolate sine of theta and we get that sine of theta equals 2 over 5 times x. So theta equals the arc sine of 2 over 5 times x. Now we can substitute this here and we get that this equals 25 over 4 times theta, that is the arc sine of 2 over 5 times x, plus 25 over 8 times the sine of the arc sine of 2 over 5 times x, and plus c, but we don't need the plus c because we are trying to find those two definite integrals. And this is our antiderivative, so we can get back to our two integrals. This is the first one. The area of the blue region is 2 times this integral, and if we call this function f of x, so this equals 2 times this integral, that is f of 5 over 2 minus f of 0, and we're lucky because f of 5 over 2 is 25 over 8 times pi, and f of 0 is just 0. So we get that this is 25 over 8 times pi, and this is approximately 19.635. We're lucky because we can get 25 over 8 times pi, because if we plug 5 over 2 here, we get the arc sine of 1, and we can get this magnificent precise result. While for the green area, we have that this is the integral from 0 to 5 over 2 of our function, that is simply half the area of the blue region, that is f of 5 over 2 minus f of 0 minus 2 times f of 5 over 2 minus f of 5 over 4. And this is approximately 2.140. Now we have the area of the blue region and the area of the green region, so we can finally get back to our area pumpkin, and this equals 4 times the area of the blue region, that is 19.635 plus 2.140, and this equals 87.1, and we are done. This is the area of our pumpkin. Okay, so it was tough to find it. We had to do plenty of integrals, and it was fun. It was so fun. I think this is a fantastic result because we had to use calculus, we had to use a lot of things to get to this result, and it was magnificent for me. We were even lucky to get 25 over 4 times pi, and let me know what you think about this. Let me know in the comments if you enjoyed this video and if you would like to see other videos like this. If you enjoyed this video, leave a thumbs up, share it with your friends, subscribe to my channel, and don't forget to watch my other videos. And as always, until next time, bye.